Radar system design is a challenging task that suffers from many trade-offs. For example, high-range resolution radar needs large signal bandwidths. A second trade-off is between the dwell time and the Doppler resolution. Another design trade-off involves angular or spatial resolution and the number of antennas in radar antenna arrays. This is why we created a new technology based upon a novel approach in sampling theory called sampling. In the sampling framework, only the content of a few narrow bands is sampled and processed by the radar receiver. A typical radar signal scenario consists of targets, clutter, and noise. The composite signal is then sampled at a low rate via sampling. Our advanced processing method then recovers the delayed Doppler map of detected targets. Our technique paves the way for a cognitive radar which shares its spectrum with other communication services without any degradation in performance. We transmit only in those narrow frequency subbands that are sampled by the Sub-Nyquist radar receiver, allowing the holes to be used by other comm services. For example, here the radar signal is transmitted in 4 different subbands in the spectrum shared with other services. The transmit power in these 4 bands is higher than a wideband radar signal. The received signal in the antenna is sampled only in 4 subbands by the Sub-Nyquist radar receiver to produce a delayed Doppler of detected targets without loss of resolution. Our advanced joint processing then recovers the ranges and Doppler velocities of targets in both directions at a native Doppler resolution, but shorter dwell time. Our Sub-Nyquist techniques can be applied in spatial domain to recover the target azimuth using thinned antenna arrays. The prototype's cognitive Sub-Nyquist 4x5 MIMO array reduces the combined spectral and temporal sampling rate by 87.5% and performs better than the non-cognitive Nyquist 8x10 array for a given target scenario.